Good afternoon. So we are finally up to Friday today, and we are ready to start doing some three-dimensional work. Before that, there was one more, this last exercise that was remaining. So something that we actually had to do. I promised you to do this one last exercise, and then we will move on to the equations of planes in three dimensions. How to describe a plane in three dimensions. And now, let us see with this. Okay, from current slide. There we go. And here we have an equation. And we need to understand what curve this is. So in principle, because we say that we have y square, the square of the y coordinate, but no square of x, we might think that this looks like a parabola because the parabola was the only case, the only situation where one of the variables did have a second order, did have a power 2, and the other variable did not. But as we can see, we also have not only y squared, but we also have 4y. So this linear term for y, which basically means that we need to somehow complete the square. If we ever have these linear terms along with quadratic terms, we try to complete the square. So this would mean y squared plus 4y, and to complete the perfect square, we need plus 4. Then we will have y plus 2 squared. On the right hand side, 2x, and if I added an extra 4 on one side, of course I need to add the extra 4 on the other side as well. And so on the left hand side I have y plus 2 squared, and on the right hand side I have 2 times x plus 2 simple. Just like this. Now, this is a very interesting situation because if we simply had y squared equals 2x, we would know what to do. We know that this is a parabola. This is a parabola. 2p equals 2, which means p is 1 and p half is 1/2. That would be the location of the focus on the, as we see, positive x-axis. Remember that whenever we have an equation y squared equals 2px, this means the parabola opens horizontally in the positive direction because all depends on that coefficient. And in this case, the coefficient 2 is positive, so it opens in the positive x direction. So we would say, all right, this is 1/2 on the x-axis. This would be, okay, this would be 1 minus 1 on the y-axis. This would be 1 on the x-axis. So if x is 1/2, then y squared is 1, and y is positive or negative 1. So we have points here, and we have a point there. And we can sketch this parabola actually quite easily, although approximately, not very accurately. Not the easiest thing to do on this board, but okay. So we have this parabola. This is the parabola. Y squared equals 2x. That would be this parabola. However, what is the difference from the parabola that we have actually obtained there? The difference is that we have plus 2 added, so 2 added to y and to x. So let us remember that in fact, we can have a parabola having y minus y0 squared equals 2 times x minus x0. This simply meant that the parabola is actually moved by the vector x0, y0, as always. So with all curves, if we have subtracted some numbers everywhere from x, everywhere from y, it simply means that if it's the same number everywhere, it simply means that the curve is moved by that vector. But as we see, then this vector would be minus 2, minus 2. Because we have added, so we have plus 2, because we have plus 2 here, and plus 2 here, plus 2 here. This means that because we have to think about subtraction, that means we are subtracting negative numbers. So this means that this parabola should move its vertex from the point 0, 0 to the point minus 2, minus 2. But let us remember what we did last time with that hyperbola or the ellipse. What did we have last time? We had a hyperbola. So we moved it, not the hyperbola, not the curve itself, but the system of coordinates. And so the system of coordinates moves, the system of coordinates moves opposite to the direction the parabola should have moved. In other words, if we think that we should move the parabola, minus 2, minus 2, so 2 units left and 2 units down, then we could say, all right, suppose we move the system of coordinates, suppose we move the axis of coordinates in the opposite direction. In other words, if I move the x-axis 2 units up and the y-axis 2 units right in the opposite direction, so the parabola would move by this vector. So this means the axis must be moved by the opposite vector in the opposite direction. In other words, this would mean that the center of coordinates, the origin, would actually move to the point 2, 2. The new center of coordinates, the new origin would be there. Actually, yes, the parabola would pass through this point 2, 2. This parabola, but in principle now, if we want to move the parabola 2 units left, 2 units down, then actually it means the same thing. We move the axis 2 units up, 2 units right in the exact opposite direction. That is, the origin actually now happens to be at this point. So we draw a vertical line at x is 2, and a horizontal line at y is 2. So this will be our new system of coordinates. In this new system of coordinates, the equation of the parabola will indeed be this. This equation of parabola, after changing whatever we got after the change, the parabola is situated like this. So the vertex of the parabola is 2 units left, 2 units down. In fact, it looks as if the parabola was originally there and then it got moved 2 units to the left and 2 units down, like this. So let me get the laser pointer. So see, if the parabola was originally here in the system of coordinates normally, then now we have moved it 2 units left, 2 units down. That is because we have subtracted minus 2 here and subtracted minus 2 there. The number subtracted, if we add 2, then the number subtracted is minus 2, which means the parabola goes from the vertex at 0, 0 to the vertex at minus 2, minus 2. Although what we actually did, we moved the system of coordinates to the new point, to the new origin at 2, 2, in the exact opposite direction. On Wednesday, I actually made a comparison. It is like a small child sitting in the train and thinking that the train stays still, but the trees are running backwards outside the window of the train. So what we did, we sort of moved the window, we moved the trees, we moved the system of coordinates to a new place, while we left the parabola where it was. And then if we move our thinking to the new origin, we have moved our thinking to the new origin, we now see that yes, it indeed looks like the parabola has been moved 2 units left, 2 units down. That is by the vector minus 2, minus 2. So we can, in fact, we could, in fact, do, let's see, I'll get red. We can think that the parabola was perhaps originally there, but then it got moved by the vector minus 2, minus 2, as supposed, as was proper, because you see the signs here are exactly opposite. We subtract some negative number, that means we get actually plus 2, we have added that number. So this is how we can think about moving these curves. If we have simplified, if we have manipulated and transformed the equation of the curve, then we actually figure out what is the vector of translation or vector of shifting of the curve, in this case parabola, and then we say, all right, let's, instead of shifting the parabola, let's shift the system of coordinates in the opposite direction. And everything works out just as well. So actually the final system of coordinates, really the real system of coordinates is this new one, the one that we moved, and we will say, okay, in this system of coordinates, in this new one that we just made, in this system of coordinates, the parabola drawn has the equation as required. It's just that instead of sketching one parabola and then moving it by the vector minus 2, minus 2, we sketch the parabola in the old system and move the system in the opposite direction. However, when we consider the situation, we will say, all right, in this red system of coordinates, in this new system of coordinates, the parabola has the equation as was given. So that's about these moved or shifted or translated curves, these translated graphs. That's something that we do normally quite often, because sketching and redrawing and moving the curves is more complicated than simply moving or drawing anew the system of coordinates. So that was the last exercise remaining from last time, the one that we didn't have time to finish up. And now we will look at a new topic, and that will be the topic about the equations of a plane in 3 dimensions. So I'm going to make a new share, plane, share, and slideshow from beginning. There we go. So equations of a plane in space. So what this means is, evidently we might have, let me check the color. I need white. So we might have, let's say, some plane, we have a 3-dimensional situation, we might have a 3-dimensional situation in 3 coordinates in the 3-dimensional space, x, y, z. So what we think is, perhaps somewhere in this space, in 3-dimensional space, we have a plane. Of course, a plane is infinite in all directions as it stretches, but when we draw a plane, we cannot really draw something infinite. So what we think is, we draw a parallelogram and we think, okay, imagine this is a rectangle, a rectangular piece of that plane, like a sheet of paper demonstrating the position of that plane. And we will try to figure out what kind of equation would describe a plane like this. For that purpose, we need to understand what is it that we need to describe a plane. So how much information do we need to be able to write down a plane, to write an equation for the plane? So let's remember that an equation of anything, of any figure, of a curve, of a line, of a plane, of a surface in 2 or 3 dimensions, means that we have an equation that only the coordinates of the object of interest satisfy. So we need an equation that in 3 coordinates, x, y, z, And this equation is satisfied only by those points that belong to the plane and not satisfied by any other points. So those and only those points that belong to the plane would fit with their coordinates into the equation. That's the whole idea of an equation of a plane. Similarly to what we had as an equation of a line or a curve in 2 dimensions. And so, let us suppose that what we have is a point of the plane, simply a point of the plane. Let's imagine that we have a plane somewhere in the 3-dimensional space. We have a point M on that plane. We perhaps know the coordinates of this plane. And then we have a vector that is perpendicular to that plane. Remember when we had line in 2 dimensions, we had a normal vector to the line, and that was the vector that was perpendicular to the line. So we had a line in 2 dimensions, and we said, all right, the normal vector is the vector perpendicular to that line. Similarly, we have a vector in 3 dimensions, which is simply perpendicular to the plane. And we call it the normal vector of the plane. So we have a vector n, which is actually perpendicular to this plane, A, B, C. That's how we think. So in order to determine the plane, we need 2 things. We need the exact direction of that plane. That's one thing that we need. And the other thing is we need at least 1 point. Okay, we can tell the direction from the vector, but where exactly that plane is situated depends on at least 1 point in the plane. So suppose we have this point M, for example, there, and suppose we have the vector n that is normal or perpendicular to the plane. And we will say that R, a random point, is just any point in the plane. So just any point, let's suppose any point R with general coordinates x, y, z in the plane. The current point or the running point, we might say, it's the point in the plane. So evidently we see we could in fact write the vector mr. The vector mr evidently is subtract coordinates of the starting point from the coordinates of the endpoint. Because the endpoint has coordinates x, y, z, and the starting point is M, that is, has coordinates x0, y0, z0, the vector mr becomes x minus x0, y minus y0, z minus z0, this one. And now the next very interesting question is, so what now? What next? Now, because the vector is perpendicular to the plane, now we have to remember, what does that mean? A line is perpendicular to the plane. We know perpendicularity. We understand perpendicularity between 2 lines. That's something that we do know. 2 lines perpendicular, the angle is 90 degrees, angle is right, we can do that. But when we have to decide how to describe that a plane and a line are perpendicular, we don't really know, because we know how to measure angles between 2 lines, between 2 directions, between 2 vectors. But how do we measure angles between a line and a plane? And the trick here is that, for example, you might imagine checking, let's say you have a pole in the field or in your yard, and you want to check whether this pole is vertical, strictly vertical. That is evidently perpendicular to the horizon. So what you do, you look in one direction, but it matches. Please switch off your microphone. But we might just have a situation where this pole looks vertical from our viewpoint, but it is actually bent backwards so that we don't see that it is bent backwards. It looks straight up. So this means that looking from this direction, we see it as strictly vertical. So to see whether it is really so, we probably will move around and check from another direction. So if it is bent away from us or towards us, then from another direction, we should be able to see it. And that basically is the general idea of line perpendicular to plane or vector perpendicular to plane. If a line is perpendicular to a plane, this simply means it is perpendicular to any other line in that plane. So if the vector n is perpendicular to my plane, it means it must be perpendicular to any other vector, any other line in that plane. In other words, it doesn't matter where the point R is. It doesn't matter in which direction in the plane. Of course, it's in the plane. In which direction in the plane the vector MR goes, because n is perpendicular to the whole plane, it must be perpendicular to any vector MR in that plane. Okay, so it has to be perpendicular, which means, now remembering vectors, this means that we have the vector scalar product of two vectors must be 0. Remember, two vectors are perpendicular if and only if their scalar product is equal to 0. Which means, yes, I have to write MR times N equals 0. But see, the vector n has coordinates ABC, and the vector MR has these coordinates. So basically what we need is we need to multiply these, we need to multiply these, and we need to multiply these. And then add everything up. Remember the definition of the scalar product of two vectors. So we get A times x minus x0, that is x coordinate of normal vector times x coordinate of vector MR, plus B, which is the y coordinate of the normal vector, times y minus y0, which is the y coordinate of the vector in the plane, plus similarly C times z minus z0. So that would be the first kind of equation of a plane in space. This means that from this equation we can read two things. From this equation, first of all, we see ABC clearly. We see the coordinates of the normal vector. In other words, from this equation, we can, in fact, determine the direction of that plane. And then x0, y0, z0 here are also numbers. So we know immediately at least one point of that plane. And so this is the first kind of equations of a plane in space. If we open the parentheses, as you see, if we open the parentheses, we have ax plus by by plus cz, and then a times minus x0 plus b times minus y0 plus c times minus z0. These are basically constants, products of constants, and when we add all those products up, you get a single constant d. So d is actually formed from these products, a minus ax0 minus by0 minus cz0. But it's a constant because the only variables, the only items, the only numbers that might change are x, y, z. Everything else is a constant in this equation. So we have a general equation. We have an equation with the normal vector and the vector in the plane, and we also have a general equation of the plane. So these equations are satisfied by and only by all those points all the coordinates of those points, which lie in that plane. If a point is in the plane, then its coordinates x, y, z satisfy this equation, and the other way around. If a point does not lie in this plane, then the coordinates evidently will not satisfy this equation. So even in this general form, the general equation form, even in this form, we can clearly see the direction at least. A, B, C is still the normal vector for the plane. This is something that we can always see. And so let's have a look at something else, something more. Now, as you perhaps remember from school geometry, or at least you should, a plane in 3 dimensions, is also determined if we have 3 non-collinear points in this plane. If I have 3 points in the space in 3 dimensions, and these 3 points are not on the same line, then we know that we can draw one and only one, exactly one plane through all these 3 points. Now, how do we deal with the equation of this kind of plane? So if we know 3 points of the plane, how do we write the equation? So in principle, again, we would take the points M1, M2, M3. Let me mark them with M1, M2, M3. And we might think of 2 vectors M1, M2 and M1, M3. So the vector M1, M2 has coordinates evidently x2 minus x1, y2 minus y1, z2 minus z1. So far, so good. Similarly, the vector M1, M3 also has coordinates x3 minus x1, so endpoint minus starting point coordinates, y3 minus y1, and z3 minus z1. And at the same time, if I have this point R, that is any other point in this plane, any point in this plane, let's mark it with, let's say green. So just the point M in this plane. So the vector M1M. So from the given point M, the M1, the point that we know, this is not M, but it's R, sorry, R. So the vector M1R, the vector would be, because R is any point, x, y, z in the plane, then I have x minus, again, starting point M1, so x minus x1, y, that could be any point in the plane, minus starting point y, y1, and for the third coordinate, exactly the same thing. So now I have 3 vectors in this plane. 2 of them have fixed coordinates because we have those points given. We know these 3 points. And the third vector has x, y, z involved. So the trick now is to remember something from the vectors. And there was a rule about vectors. 3 vectors are actually collinear, not collinear, but coplanar, that is linearly dependent, if and only if the determinant formed by the coordinates of all these 3 vectors was equal to 0. So right now, the determinant formed by the coordinates of these 3 vectors is actually, so I'm repeating, I actually wrote what I was just saying. So any 3 vectors in the plane are linearly dependent, because any vector, if we have 2 given vectors like M1, M2 and M1, M3, any other vector in this plane can be expressed using the 2 given non-collinear vectors. And linear dependence meant determinant made from all the coordinates of these 3 vectors is equal to 0. That was from vector topic. That was from the vectors unit. So this means that the vector formed by the coordinates, see, in the first line, in the first row of this determinant, we have the coordinates of vector, okay, I will do this way, the vector M1M, In the second row, we have the coordinates of the vector m1, m2, and in the third row, we finally have coordinates of the vector m1, m3. And that's more or less it. That's more or less it. So we can, in fact, say this looks awful. This looks rather horrible, right? It looks really messy. It's big. It's clumsy. Now that's so much writing because we have 9 positions. We have 9 positions, and in each position we have to write 2 coordinates. Some of them are known and some of them are not known, but we have a lot of writing ahead. So we need to remember that these are all numbers except for x, y, z. X, y, z are variables, but x1, x2, x3, y1, y2, y3, z1, 2, 3, they are numbers. So in principle, we will only have unknowns. We will only have variables here in these 3 places. But everything else is a constant. Everything else is a number, which means we can easily simplify this. Or we could start by finding the 2 vectors, m1, m2, and m1, m3, writing them, finding the exact coordinates of these vectors, like in numbers, 3, 2, 4, 1, minus 7, 0, for example. And then you would simply write the coordinates of those vectors here in the last 2 rows of this determinant. There are more interesting connections. For example, actually, when I use these minors, when I use these last 2 rows, I can actually find the 3 coordinates of the vector product of the 2 yellow vectors, m1, m2, and m1, m3. The vector product actually works as the normal vector of this line because it's perpendicular of this plane, because it's perpendicular to the plane. So it will work as the normal vector if I find the vector product. And then basically I can complete this, the mixed product, which will actually give us the equation. It will give us the equation of this plane. So the equation of the plane is evidently the mixed product of these 3 vectors, m1r, m1, m2, m1, m3, the mixed product of these 3 vectors. And you remember that if the mixed product, the triple product of 3 vectors is 0, then these 3 vectors are in the same plane. So in principle, this is the triple product of vectors. And so what we see in this situation is that we can write in the vector form, we can write the same equation in vector form, but basically we understand things much better if we have numbers and x, y, z. So that's why we will use this form for the determinant. However, yes, we can find the 2 vectors separately, so that we can actually plug them into the equation of into this determinant. So this is number 3. This is the third equation, third kind of equation, which means that we can write an equation if we know 1 point and the vector perpendicular to this plane. We can write an equation if we have 3 points in the plane that are not collinear, so they don't lie. The 3 points don't lie on the same line. So equation of a plane through the 3 given points. And let's see, there is one more. There is one more. So these are the 3 that we have so far. These are the 3 that we have so far. At the same time, yes, we can understand that the normal vector of a plane can be found as m1, m2, vector product m1, m3, because this will be the vector that is perpendicular to the vector m1, m2 in the plane and m1, m3 in the plane. If these 3 points are the 3 points in the plane, then evidently the normal vector should be perpendicular to both those two vectors in the, so this is the normal vector, has to be perpendicular to both the two vectors in the plane. So it has to be perpendicular to this and perpendicular to this. We know that the vector product has such property. If I find the vector product of these two vectors, m1, m2, and m1, m3, then this vector product should be perpendicular to the plane. That is, it works very nicely as the normal vector. We can use that. So basically, it's the same thing as writing the equation through 3 points. And there is one more, that is plane through the segments, cutting off the segments of the coordinate axis. For that, to understand this fourth equation, number 4, we need, again, a little sketch, a new one. So we assume, again, that we have the 3 axes of coordinates, x-axis, y-axis, and the z-axis. And we have points A, B, C on these 3 axes. Suppose we have 3 points, like this is A on x-axis, this is B on y-axis, and this is C on the z-axis. We can imagine that we have a plane passing through these 3 points on the axis. And of course, yes, it cuts the system of coordinates, the plane of coordinates along these lines. What we see in this first octant of the system of coordinates is just a piece of that plane, which is triangular, and you can imagine how this plane intersects the planes of coordinates. And so what we actually get to see is only this little triangle, because everything else from that plane goes further away. So again, A is the intersection with the x-axis, as always and ever. B is the intersection point with the y-axis, and C is the intersection point of the plane on the z-axis. So this is the fourth kind of equation of a plane in space in 3 dimensions. Now let's have a look at what can be done with this. Why do we need equations of a plane? What could we do about these equations in the plane? So right now we have moved from 2 dimensions to 3 dimensions. So a 3-dimensional situation is always harder to understand, and that's why we need to be very, very careful. So how do we use these plane equations? One application could be finding the angle between 2 planes. The critical moment, suppose we have 2 planes given with general equations. So in principle, we will normally assume that we have general equation for a plane. If we have any other type of equation, yes, of course, it is possible to transform it into a general equation. So now let's suppose we have 2 planes. It looks something like this. So we have an equation. We have one plane, let's say this one in yellow, and then we might have another plane, that other one in green. Let's suppose this plane is in green. And then we have the intersection line. You know that 2 planes intersect through one line. So we are looking at these 2 planes, and we think, okay, suppose we have these 2 normal vectors, normal vector n1 and normal vector n2. Now, if we look at the situation, see through the line of intersection. In other words, we look in this direction, so that the line of intersection actually looks like a point. We are directly looking in that direction. So here we see the 2 planes again. The green plane, that would be this one. only now we are looking at it from the edge from one side, and then we might have this other. Okay, sorry, it's this plane. This plane, and we need to find the angle between these two planes. The angle between these two planes, as we might think, as we can see, is in general the angle between the two normal vectors. It is the same angle between the two planes and between the two normal vectors. However, we should understand that the normal vectors might sometimes form an angle that is obtuse, greater than 90 degrees. However, the angle between two planes is the smaller of the two angles that we can find here. So in principle, the angle between normal vectors could be obtuse, but we still need the acute angle less than 90 degrees, and therefore we have to be careful. But other than that, how do we find the angle between two vectors, n1 and n2? Of course, using the scalar product, just like we did. So the scalar product of vectors n1 times n2, see the scalar product here, we divide it by the product of the magnitudes of the lengths of the two vectors. And yes, it might be negative in the end. If the cosine is negative, remember that means the angle is obtuse, greater than 90 degrees. By definition, the angle between two planes is at most right if the two planes are perpendicular, but we are in general considering the acute angle, the smaller angle. And this is why we put this absolute value here again, because remember, if we have two angles on a line, two angles on the same line, that actually means that the cosines are opposite values. So the cosine of this angle and the cosine of this angle, because they both form together, they form a straight angle, the cosines are simply opposite numbers. And therefore you make sure that the cosine value is positive to get the acute angle. So just like that, we only take the two normal vectors of the planes. Next, it's more than that. So we have this cosine. So in general case, we have the cosine of the angle expressed using the normal vectors. Secondly, two planes can be parallel if and only if the normal vectors are collinear. They don't have to have the same normal vector. It's quite enough that we have these vectors collinear. So one vector might be longer than the other or going in the opposite direction. But the thing is that what matters is this parallelity. The planes will be parallel if the two vectors are collinear. So in principle, what we have to do is, of course, check the collinearity. Remember, one vector and coordinates of the other vector. These vectors must be the coordinates of these vectors must be proportional. Then we can say that the two vectors are collinear. So it might sometimes happen that we have two planes and one of them is written in a slightly more complicated manner. We need to recognize that this is also an equation of a plane. Perpendicularity. Two planes are perpendicular if and only if their vectors, normal vectors, are perpendicular. But of course, if we have two planes that are perpendicular, let's say like one plane and then the other plane, so two planes that are perpendicular. So what about normal vectors? One normal vector evidently goes like this, the other normal vector goes like this. If the two planes are perpendicular, then the normal vectors are also perpendicular. There's no other option. So parallelity can be found from normal vectors. parallelity of normal vectors, and perpendicularity of normal vectors. That is, the scalar product of these two normal vectors must be equal to 0. Nothing else will help. So we have two basic ideas to remember from vectors. From the second unit in the vectors, we had actually questions like this. When are two vectors parallel? When are two vectors perpendicular? And we use those to establish connections between planes. So that would be the first application, finding the angle between two planes. What else could we do with plane equations? Distance from a point to plane. The distance from a point to plane, that would be, we might have the plane somewhere, and then we have a point, and we need to find the distance from this point to the plane. We, of course, do that using a perpendicular. We need to find the perpendicular distance from the point to the plane. Otherwise, it doesn't count as a distance in any way. So we suppose we have a point and a plane. And now how to do this? How to find the distance from the point to the plane? Two methods, just like very similar to what we did with the line and the point in 2 dimensions. Remember, we had this situation in 2 dimensions, a point and finding the distance to the line. So the first method would be find the line perpendicular to the given line, or in this case, find the line perpendicular to the given plane passing through the point P. Find the equation for the line passing through P perpendicular to the given plane. How to find that equation, that's a completely different question, because we have not yet discussed how to find an equation of a line in space, in 3 dimensions. That's a bit of a problem. But if we can find this equation for the line, in this case PF, and I would say that F is the foot of the perpendicular. That's why I put the letter F. So F is the intersection point, but we need the direction vector for this line and a point on this line P. When we have this equation, we will find the intersection of this line and this plane. And when we have the intersection point F, and we already know the point P from the very beginning, we can find the distance between the 2 points P and F. Or if you like, you can think in terms of vectors, it would be the length, the magnitude of the vector PF. And that's the distance. However, there is a second formula, and this formula again is very similar to the formula of distance we had in 2 dimensions, line and point. So with plane and point in 3 dimensions, the formula is very, very similar, it turns out. And it is this. So what is different from the line in plane, what is different from this situation, is that we have a little bit more coordinates. The normal vector is ABC, so now it has 3 coordinates, but we still also use the free term D very similarly. So in the case of a line in plane, we did not have, and this had to be Z, we did not have this and we did not have this. And then we had the distance between a point and the line in the plane. And I also have to note that I have made a little bit of error. We need Z0 here, of course. It is Z0 here. So we put the coordinates of the point into the equation of that line, of the plane, and write this expression above the line in the numerator. Then we find the absolute value, the modulus of the normal vector of the plane. and divide this. So it's very similar to the situation in the plane where we were looking at the distance from point to line. Very, very, very similar. And again, we do this depending on whether we need to find the point F. Is it required? If the only thing needed is the number, the distance, then of course we use method B. We use the ready-made formula. If we need to find the point F, if we perhaps need to find the symmetrical point like we did with the line, then of course method A would be better. And now some exercises. Let's have a look. Okay, just a moment. All right. I was just checking the time. So, given 2 points, find the equation of a plane perpendicular to the line M passing through M. So suppose we have 2 points, M and N. We have the line MN, and we need to draw a plane that passes through the point M and is perpendicular to this line. So what we need is, we have point M, so we have the coordinates of a point in the plane, and what we need is the normal vector. It seemingly is not given, but we see we can use vector Mn as the normal vector. So let's write it down. The normal vector would be 4 minus 2, 0 minus negative 3, and minus 2 minus 1, that's minus 3. This is the normal vector. And now, using the point M as the given point, remember that the vector MR is the vector x minus 2, y plus 3, and z minus 1. Remember that all we have to do is write the equation in the form a times x minus x0 plus b times y minus y0 plus c times z minus z0. That was the general, not the general, but an equation using normal vector of a plane passing through a given point. So now, A, B, C, those are the coordinates of the normal vector. So I'll write 2 plus 3 minus 3 instead of ABC. And now I need x minus x0, but we will consider this the point with coordinates x0, y0, z0, because it passes through M. So it will be x minus 2, it will be y minus negative 3, which becomes y plus 3, minus c, which is z, minus 3, times z minus, evidently, 1. We are using point M. We are using coordinates of point M. Equals 0. Now we can simplify this somewhat. So this is the equation through the point perpendicular to the given vector. Now, to simplify this, we can open the parentheses, 2x plus 3y minus 3z. Now, let's add these numbers up. Minus 4 plus 9 is 5, and 5 plus 3, the product, is 8. So it's plus 8 equals 0. When I open the brackets and I pull together all the separate constants, like 2 times minus 2, 3 times 3, minus 3 times 1, and I can write the equation for the plane using simply the normal vector and the constant d, which is simply a constant that pulls together the 3, let's say, remaining factors, the remaining products, so that the equation is simpler. Both these equations are perfectly correct. I will accept one or the other, doesn't really matter too much. So these two equations, in principle, They mean the same thing. In one case, the parentheses are opened and the numbers are taken together. The like numbers are combined. In the other case, it's just we see the point and we see the normal vector. Both are perfectly right. So there's no limitations unless a quiz or a homework or a task states, write the general equation, write the equation through point with a given normal vector, and so on. So in principle, usually we do this simplification, yes. And that's the answer. Now, another thing. Plane passing through origin parallel to this given plane. So the normal vector of this plane, is 3, 2, minus 1. That's the normal vector. Passing through origin, it means that I could say that one point that I know in this plane is 0, 0, 0, because those are the coordinates of origin. So this can be, in fact, to substitute for x0, y0, z0 in the given general equation, or equation through the point perpendicular to a vector. So I could say 3 times x minus 0 plus 2 times y minus 0 minus 1 times z minus 0 equals 0. I am writing it in the long form because it's always necessary to explain the reasoning. So I would like to see how you get the equation from the answer. Now opening the brackets, 3x plus 2y minus 1z, everything else, 0 times whatever, will disappear. So the equation of the line that we seek is this. Right equation of plane passing through the origin parallel to the given plane. Remember that if two planes are parallel, they may just as well use the same normal vector. They might use collinear normal vectors, but they may use the same normal vector. It works. And so we just copy the normal vector from the given equation, but we put our own point in that equation. And that's perfectly sufficient. That's all that we needed. Next exercise. 3 planes passing through the point 3, 2, minus 4, and parallel to the planes, that is the planes of coordinates, and sketch them approximately. We will do that in 3 dimensions. That's a little bit messy. As you remember from vectors, sketching vectors involve those shoe boxes, the parallelepipeds. We will do the same here in this exercise. So suppose that we have the system of coordinates x and y and z, and we have the point 3, 2, minus 4, so 3 units x, 2 units y. This is in the xy plane, and then 4 units down. 1, 2, 3, 4 units down. So I have to go here. I also need to go 4 units down. And so we will have this box, just like we had with vectors. We imagine this box that has evidently 3 units in the x direction, 2 units in the y direction, and 4 units in the negative z direction. So this means that the point with coordinates 3, 2, minus 4 is this one. This is the point. You see that if we project this point to the xy plane, we get the coordinates x is 3, y is 2. And if we project this point perpendicular to the z-axis, we get to the point z is minus 4. And now understanding the three planes. So if we want to if we want to see the plane that is parallel to the xy plane. See, xy plane is this, the horizontal plane, the one that we see as the floor of the whole situation. So this means that would be this plane, the bottom part of the box. The one thing, x and y can be anything in that plane, but we see that the z value is only -4. So the first plane would be described by the equation z equals -4, or rather z plus 4 equals 0. And that's for all, that would be for all x and y values. It doesn't matter what x and what y is, because the only thing that is sure is that this plane is parallel to the xy plane, and it passes through the point -3, evidently on the z-axis, -4, sorry. Why did I do -3? I'm not exactly sure. It was -4. It was -4. I will write it more clearly, that's all. -4 is this point on the z-axis, and that's this plane. So the first equation, z plus 4 equals 0. That is the one parallel to the xy plane. Now the next one, if a plane is parallel to the xz plane of coordinates, that would be xz, that is this plane passing through these two lines. So this means that we need this particular plane as parallel to the plane xz. And we see that it again passes through the same point, and basically for all x and z values, the y value will be equal to 2. All the points of this plane will be at the distance 2 units from the xz plane. So I can write the equation. Evidently, y must be equal to 2, or I can say y minus 2 equals 0, this way. So this is the equation of a plane parallel to the existing plane of coordinates, or we could say perpendicular to one of the axes of coordinates. And finally, the third plane, that would be parallel to YZ. This is Z, this is Y, so parallel to this plane there. So that will evidently be, if we have to go through point M, then parallel to the YZ plane, that would be this vertical plane. And this vertical plane evidently passes through point 3 on the x-axis. So we can write x equals 3, or we could write x plus 3 equals 0. So these three planes and no others are the planes. First of all, given by these equations, we see that if a plane is parallel to the coordinate plane, that means that one of the axes, one of the variable values for the axis is a constant, and the other things might be whatever the other coordinates could be. For example, in this, where we say z has to be -4, that simply means that x and y can be anything in that plane. We could think in 3 dimensions, it might look like this: 0x plus 0y plus z plus 4 equals 0. So we see the normal vector is 0, 0, 1. It's the vector k. The normal vector. For this plane, For this plane, we could write 0x plus 1y plus 0z minus 2 equals 0. For this, the normal vector is 0, 1, 0. That is the vector j, remember the base unit vectors. And this is the vector k, the base unit vector. And for the third plane, we would have x plus 0y, because there's no y in this equation, plus 0z plus 3 equals 0, and the normal vector is 1, 0, 0. That is, the normal vector is I, which means basically that the plane, if the plane is parallel to the y and z axis, to the yz plane, it will evidently have the normal vector in the direction of the third axis, and so on. So it is possible, just like we are used to writing equations of a plane, of a line parallel to the axis, x-axis or y-axis, in 2 dimensions. So in 2 dimensions, that's a D. In 2 dimensions, if I have a line horizontal passing through the point, for example, 3 on the y-axis, we write the equation of this line is y equals 3 for all x values. Just like here, for the plane parallel to the x and y axis, or the xy plane, we say, okay, so z equals minus 4 for any xy values. So it's just that the number of variables is greater. And if I have an equation of a vertical line, for example, passing through a point minus 2 on the x-axis, then the equation would be x equals minus 2. Again, something very similar to what we have here. The situation is similar. So if we need planes parallel to the coordinate planes, then that simply means the equation becomes very, very simple. Only one of the variables is involved. So something like this. Something like this. So in principle, it is easier to sketch these lines. See, I didn't sketch them separately. I sketched these lines basically looking at that box as the faces of the box, as the sides of that box. So this was the line, this was the plane parallel to the YZ axis, YZ plane. The darker yellow, the orangey thing, was parallel to the XZ plane, and the bright yellow one, this in the bottom part, this was parallel to the XY plane. So this is perhaps the easiest way of sketching planes that are parallel to the coordinate planes. And now, okay, that's something I didn't need to do. Next, are these 2 planes perpendicular? How do we know that? We take the normal vectors. We take the normal vector of one plane. We take the normal vector of the other plane and check if these normal vectors are perpendicular. Then the planes themselves, of course, must also be perpendicular. So the normal vector of the first plane is 4 minus 5, 3. The free constant, the free term, does not influence the normal vector. It is simply a constant in the equation, but it does not have any relation to the vector. The vector has coordinates only the coefficients of the variables. And for the second line, we have 1, which is the coefficient at x, minus 4, minus 1, which is the coefficient at z. Now let us check. So n1 times n2, the scalar product of these vectors, is it 0 or is it not 0? So let's see. 4 times 1 minus 5 times minus 4 plus 3 times minus 1. This is 4 plus 20 minus 3. No, it's not equal to 0. So we say these planes, no, these planes are not perpendicular. not perpendicular. Because if those planes are perpendicular, then the normal vectors would be perpendicular and the scalar product would be equal to 0. It's not. So the planes are not perpendicular. This is, let's say, kinda, sort of very simple problem. Again, next one. Write an equation of the plane passing through 3 points. Now this is where we can use the determinant. This is where we can use the determinant. Remember that form that looked rather horrible. That was x minus x1, y minus y1, z minus z1, where x, y, z are variables, but x1, y1, z1 are the coordinates of one of the points. One of the points, for example, of A. Then we have x2 minus x1. Now this will be a certain vector starting at the same point, A, but let's say going from A to B. So these are the coordinates of the vector AB. These are the coordinates of vector AM, where M or A are, let's say, R is the random point in the plane. And finally, the coordinates of the vector AC, that would be x3 minus x1, y3 minus y1, and z3 minus z1. And this huge determinant must be equal to 0. So this means what we have to do, we simply have to fill in now the numbers. So x minus 0, y minus 4, z minus -1 means it's z plus 1. Now see, these are all the same. Now x2, that would be 3 minus 0, 2 minus 4, and z is 1 minus -1, that is plus 1. And finally, bc, from C coordinates, subtract B coordinates, minus 1, not BC, but AC, I'm very sorry. From C coordinates, subtract A coordinates, minus 1, minus 0, 6, minus 4, and 2, minus -1, which is plus 1. I would agree. I know what you are thinking at this moment, and I would generally agree with you. This looks awful. This looks rather complicated. So what we will do, we will simply open this. So we will at x, y minus 4, z plus 1. Then we will have 3 minus 2, 2, and we will have minus 1, minus 2, 3. Now this is better. So still better, it would be still better if we would open this determinant, that is expand, and we would best of all expand it through the first row. So that's a lot of work, as you can see, quite some work. So we would have x times the corresponding minor, that is this part, minus 2, 2, minus 2.
Sorry, last number of second column should be 2.
Last number, I wrote minus, so yes, plus 2. Okay, I'm writing plus 2, so it's plus 2 now. All right. Thank you. Now, minus, remember, y minus 4 times determinant 3 minus 1, 2, 3, and plus the third element, z plus 1, in order to create that minor, the correct cofactor. And now we have 3 minus 2, we have minus 1 and 2. So 2 is now correct. Now I put this correct number. I corrected this. Okay, so now it has to be equal to 0. So now we should evidently open this. So minus 6 minus 4 is minus 10x. Here we have 9 minus -2 is 9 plus 2 is 11. So we have minus 11, y minus 4. And what else we have? Plus 6 minus 2 is 4. 4 times z plus 1 equals 0. And then we can open up and make the general equation. So it would be minus 10x minus 11y plus 4z, and then we have 44 plus 4, that means plus 48 equals 0, something like this. See, that's quite a lot of work. First of all, we need to recognize the correct form, the determinant with a lot of numbers in, and then we have to open it up. An option, another possibility, think of it like this. Another possibility would be, imagine this plane, imagine the 3 points A and B and C. So we have AB and we have AC. We could think the normal vector for this plane should be perpendicular to AB and also perpendicular to AC. That is, why don't we find the normal vector of this plane as the vector product, normal vector as the vector product. Remember, the vector product was perpendicular to both. The vector product AB times AC. And interestingly enough, the coordinates of the normal vector would actually come from these. Remember that we have vector AB and we have vector AC as the second and the third row coordinates in this determinant. So if we do these things, these are actually coordinates of the vector product. So that would be another possibility. That is, first of all, write vectors AB and AC separately. That is, do not write them in the determinant, but write them separately, these two vectors. Then find the normal vector as the vector product of these two vectors. You would get the same numbers. Minus 10, minus 11, and 4. From the vector product, actually, you would get these numbers. You would get these numbers for vector product. Minus 10, minus 11, and 4. And then you could simply say, okay, x minus x0, y minus y0, z minus z0, put any single point, any one point instead of x0, y0, z0. And you would still get exactly the same equation. So in principle, passing through 3 points can be resolved in two different ways. Basically, the meaning of this all is exactly the same. It's just that here, with the determinant, we do it all at once. We write the final form, we write the form at once, and then we simplify it until we get this. And in the second case, we first find vectors AB and AC, which would actually be these numbers, these coordinates. Then we find the normal vector by vector product, which would actually be these numbers. And then we would just write the equation. Minus 10 times x minus 11 times y minus 4 plus 4 times z plus 1. So it can be done in different ways as long as you understand what is going on. You may use the ready-made determinant, or you may use the idea that a normal vector should be perpendicular to the two given vectors, which means you may just as well take the vector product. All right. Now, the equation for a plane passing through a given point and parallel to two given vectors. That is, if I have the plane M, the plane P, whatever the plane P is, it has to be parallel to the vector A and to the vector B. We will imagine that we place these two vectors in the plane. This means exactly the thing I did before. This means that the normal vector of this plane is perpendicular to both A and B, It means that the normal vector can be found as the vector product, vector A times vector B. Simply finding it as a vector product. So let us see, 2, 3 minus 1, 1, 0 minus 2. Let's find the vector product. The first coordinate is, we pretend to cross out the first two coordinates, use only the remaining part, use only the second and third coordinates. So the first coordinate would be minus 6 minus 0, that's minus 6. For the second coordinate, we simply pretend that these second coordinates are not there and we use the remaining ones. Minus 4 plus 1 is minus 3, but remember that for the middle coordinate we had to change the sign for the vector product, plus 3. And finally, for the third coordinate, we cross out the third coordinate and we only use the first and second. 2 times 0 is 2, minus 3 is minus 1. So the normal vector is minus 6, 3, minus 1. This is something we can use as a normal vector for that plane. And now, yes, quite right, we say minus 6 times x minus something, plus 3 times y minus something, minus 1 times z minus something equals 0. That would be through the vector n, perpendicular to the vector n and through the point M. So point M has coordinates 1, minus 2, 2. So that's what we put in there, minus 2, minus negative 2, and minus positive 2. That is already an equation of that plane. If we want to simplify, we write minus 6x plus 3y minus z, and now the constants. 6 plus 6 is 12, and plus 2 is 14. Yes? Can you... Okay. And if we don't like to start the equation with a minus sign, we can just as well change all signs if you like, multiply the equation by minus 1. If you prefer to start the equation with a plus sign, then you can simply change all the signs in the equation to opposite. Also, if you find, for example, that the normal vector has all coordinates even numbers, divisible by 2, what we do is, yes, we can divide everything by 2. If we have the normal vector coordinates all divisible by 5, why not? We can divide all coordinates everything by 5. That's not a problem. So we can always, if possible, it is quite okay to simplify the equation, to multiply or divide by a number that makes everything simpler. Oh no, this doesn't look very good, at least for me, if I'm very close to this screen, but let's see. The normal vector of the first plane, 1 minus 2, 2. The normal vector of the second plane is 1, 0, 1. Very careful, because x has coefficient 1. Y has coefficient 0, there's no y, and z has coefficient 1. See, minus 6 has nothing to do with the direction with the normal vector. We have these coordinates for the normal vector of the second plane. So a reminder for you, if one of the variables is missing, the corresponding coordinate of the normal vector is 0. And the numbers themselves, like minus 8 and minus 6, have no influence on the angle, because these numbers simply tell us, to some extent, where these planes are situated. The angle, the direction, is completely determined only by normal vectors. So the angle, okay, that was cosine of the angle was, remember, the scalar product of the two vectors, which is a number, divided by the, okay, I will write it slightly differently. The magnitudes of the two vectors. Magnitudes of the two vectors. I don't want to write the square roots immediately. And then if I see that this threatens to be negative, in that case, we simply put the absolute value on it, because remember, this should be positive to make sure that the angle is acute angle, it's not obtuse. All right, so we can do it separately. The scalar product of the two vectors, 1 times 1 minus 2 times 0 plus 2 times 1 is 1 plus 0 plus 2, it's 3. All right, positive. No need for the absolute value sign. Now the magnitudes. The magnitude of the first vector, square root, 1 square plus 2 square plus 2 square, that would be 9. That's 3. Okay, 3 times, and for n2, we have square root of 1 square plus 0 square plus 1 square. That is square root of 2. Okay, square root of 2. What we see is 1 divided by square root of 2, also known as square root of 2 divided by 2, if we don't like roots under the fraction bar in the denominator. This means the angle is 45 degrees, the angle between the two planes, because the angle between the two normal vectors is that. And we remember that the angle between the planes is exactly the same as the angle between the two normal vectors. And so we have the answer. Now let me see. At this moment, we have something like 1 minute remaining, and it looks like we are finished with this. Absolutely perfect timing. For the first time, I have finished exactly on time and exactly the whole thing. Next time, so first of all, please remember that here in Latvia, we are changing the time this weekend. So Saturday night, we are turning our clocks 1 hour forward, which means when we have 10:15 in the morning here on Monday, your normal time, the normal time actually is 1 hour earlier, because we move our clocks forward. So those of you who are here in Riga or in a country where you also turn the clocks this weekend, nothing changes. But if you are in a country that does not change the clocks, then you should mind that on Monday, the lecture for you will start 1 hour earlier, because what will be a later hour for us, actually, because we turn the clock forward, will be earlier for you. So if I want to get up, for example, at 6 in the morning on Monday, it means by today's measure, I will be getting up at 5, 1 hour earlier. So please remember that. So the timing changes slightly. Please make a note, because that otherwise you will be late. You will miss the lecture or the greatest part of the lecture. So please make sure you get the time correct. We are moving to summertime, so on Monday GMT plus 3 hours. Okay, then I will talk to you all on Monday. By that time, I will be finished with marking your vectors unit test and uploaded. I don't want the reason why I have not uploaded, I don't have that much remaining, but I want to upload all the marks at the same time. I don't want to upload, let's say, 1 at a time, or 5 people get the marks and then 10 people don't, and so on and so on. So I have just a few papers remaining. When I finish marking those, I will release all the marks at the same time for everybody. So far, so good. On Monday, we will talk about lines in 3 dimensions. And then on Wednesday, we will talk about lines and planes in 3 dimensions. And then after that, we are going to have the unit test. All right. So have a nice weekend, have a good rest, and we'll meet on Monday.
Thank you, Professor.
Thank you, Professor.
You're welcome.
Bye, ma'am.
Goodbye.
Thank you, ma'am.
You're welcome.
Thank you, ma'am.
Thank you, ma'am.